Hi, this is Raclette Group 1 presenting classification of eco fingerflex paradigms with deep learning and discussions of motor preparation. These are our group members, Xin, Vitto, Hobart, me, Doris, and Xin. Let us get started by understanding the behavioral paradigm and basically the experiment a little better first. It is a very simple movement trial that is done, that cues are presented on a monitor that the participant has to react to. A data glove, a 5-degree of freedom sensor is there, and it records the position of the fingers, and then that behavioral data is normalized, and this is the raw time series that was provided to us. So basically the movement trials are interleaved with rest trials, movement, and there are 30 such movement cues for each finger, and the trials are chosen in random. So this cartoon shows this interleaving of movement and rest trials. Rest trials are basically a blank screen in much more vividly. So let's start with the first subsection, which is CNN CAM fingerflex classification. Over to you, Xin.
Okay, thank you. So in this part, what we want to do is to first train a convolutional neural network using ACOG data recorded from each child to do a 5 classification task. Each task corresponds to a finger. After we finish the model training, we use the fixed weight in a fully connected layer and the feature maps in the last convolution layer to do class activation mapping. Specifically, we perform global average pooling before the fully connected layer, so that each unit in the fully connected layer corresponds to a feature map in the last convolution layer. We use these ways to get a weighted average of the feature maps, and that is the class activation map we wanted. This activation map can tell us the magnitude of the contributions from each electrode. The larger the contribution, the more important this electrode is to our classification task. So in the next slide, we present the CAM results from the thumb and the little finger, which shows distinct difference. We selected top 3 electrodes and their locations. The brain regions where these electrodes are located are near the motor cortex, which means our results have anatomical and functional evidence. Our conclusions is that the thumb and the little finger flexion are easier to classify. One hypothesis is that thumb finger doesn't pull other fingers during flexion, while little finger pulls the most. They're like 2 extremes, which separates them from other fingers. The electrodes and brain regions related to thumb flexion and little finger flexion are spatially close, and that is all about this part.
Okay, so the next section is on motor preparation across the finger data. So here's some quick definitions. So we wanted to look at motor preparation or attention in the context of some literature that found that there's a high possibility that wrong responses are caused by low attention levels or large attentional variations. We studied alpha, beta, and theta frequency bands. Alpha and beta bands are usually linked to shifts in attention, whereas theta bands are linked to intuition and decision making. Next slide. So we examined motor preparation after the cue onset. This picture shows the correct trials and response time distribution across fingers. Next slide. We extracted event-related potentials, or ERPs, after the cue onset for all fingers, and several electrodes in the frontal and parietal regions. Those electrode data samples reveal that there are some regions or electrodes that are more active than others. Next slide. So here are some time frequency plots. We looked at 2 electrodes, one in the frontal and one in the parietal lobes. This is data for the thumb finger flex. So electrode 35 in the frontal lobe had a beta band at the beginning of its time period, and then the parietal electrode 39 had a theta band at the beginning. So this shows the beginning of motor preparation. Next slide. So now, as opposed to the thumb, we look at the little finger flex for the frontal lobe. we observed no significant bands and equal power among the different frequency bands. For the parietal lobe, we saw a dominant beta band. So these are just examples to show how we can qualitatively make claims about the attention states based on beta bands and alpha bands that we observe, but there's no statistical verification or significance checking here.
And the third sub-project is mainly about the wrong responses and attention. In the ECOG fingerflex dataset by Miller, we noticed that the participants sometimes flex different fingers from what the cue on the screen is. So based on their wrong response subsets in the dataset, we assume that there is some modulation or switch in the attention state. And as mentioned before on the attention, an investigation of participants' response time is fairly standard in the study of attention, which helps visualize their patterns. And also, attention could also be characterized by spatial temporal dynamics of the alpha oscillation. So looking at some typical patterns that we found during the pre-data process, we know that the orange color is a visual cue signal and the blue is a patient's response. So here we can see that only number 1 is a typical correct trial, a response tightly after the cue. And only the number 3 here is the wrong trial under our definition, like they flex the wrong finger. And others, they either respond too late, there's a delay, or just a mess, which they're not counted for the wrong trials in our study. Next slide, please. Yeah, so overall, we use the response time, alpha band, and theta band activity and between the frontal and parietal areas as a criteria for the correlation between the attentional level and the correct or wrong responses.
Yeah, so the first criteria we need to pay attention to is the response time here. And first of all, what we do is we want to do whether the peak of band power is highly correlated with response time. And the thing we found out here is that the theta band is really a good thing we need to pay attention to because they have a significant relationship with temporal lobe, which temporal lobe is in charge of object recognition, and the theta band will be related with decision processing. So here what we found out is that these two is correlated, but in the alpha band, although we find some significant related electrodes, but actually they are not really localized tightly. So it's really hard to say that whether there is any brain area that's really had related with it. But unfortunately, we didn't really find the relationship between response time and the crack or wrong trial. But we think that is what we need to do in the future where we could do more better in the experiment diagram. And the next one. So in the next slide, what we show you guys here is we did like cross-brain analysis. In the cross-brain analysis, what we do is in different alpha or like theta band, we try to analyze the difference of power spectral density in across different brain area in both correct and wrong trials. So the PSD correlation map here shows that we could see that the frontal and parietal area in theta band and also parietal and temporal area are highly correlated with other. And in the alpha band, which the highest correlation happens in frontal and ventral sensory motor. So what we could dig into in the future is the parietal frontal area connectivity, temporal parietal, and frontal and ventral sensory motor. So in the next slide, what we want to do is still like an ongoing process. It's the cross-frequency coupling. And it will be really appealing that we could do cross-frequency coupling between fast wave and low wave. The fast wave we mentioned here is a beta wave, and the low wave, slow wave here would have mentioned it theta wave. And although we're still working on it, but there are already some like significant pattern we could find out, but we just don't have time to do the future processing. So here we could see what I show here is the plotting of the parietal of the certain electrodes in parietal area, which got like obvious pattern. So in electrode 29, we could see that they're really interesting to dig out in the future. And I think that's all. Thank you guys for listening. And if you want to have any questions, please feel free to reach out to us. You can find our project and our contact information in the down below link. Thank you all again.